The binomial theorem is an amazing and powerful tool. However, it can also be kind of confusing to use. And even though it's quicker than multiplying, we still might want something even quicker than the binomial theorem. So is there a way to generate binomial coefficients if we don't want to use combinations? And we can, technically we can. Underlying this method, combinations come back, but we can generate these numbers without using our calculator and without using the binomial theorem by using Pascal's triangle. So this animation, which I found online, I am eternally grateful for whoever made it, shows us how we begin to build Pascal's triangle. We start with 1, and then we add 1 and 1, and then each new number is the sum of the two numbers above it. So 1 and 1 gives us 2, 1 and 2 gives us 3. All of these ones on the outside, we can think of it as 0 plus 1 is 1, 0 plus 1 is 1, 0 plus 1 is 1. And so we'll watch through this once more, and then we'll look at an expanded table of Pascal's triangle. So on this slide, we can see Pascal's triangle all the way down to the 7th row. So we have 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1. You might recognize these coefficients from the example in our last video. 1, 5, 10, 10, 5, 1. Notice also that the first non-1 digit corresponds to the power of n in our binomials. So if we want to expand x minus 3, using Pascal's triangle, we first need to go to the first row that has a 3 in it. So we start 1, 1, 1, 1, 1 plus 1 is 2, 1, 1, 1 plus 2 is 3, 2 plus 1 is 3, and then 1. And I think I said a moment ago we had to go to the first row that has a 3 in it. I meant to say 4. We need to go to the first row that has a 4 in it. So 1 plus 3 is 4, 3 plus 3 is 6, 3 plus 1 is 4, and then 1. And we can see this is the row that we want. We have to go no further, and we're also not going to use any of those numbers on top. All we need is this one at the very bottom. So I'm going to spread out my coefficients 1, 4, 6, 4, and 1. And I'm going to put a plus sign in front of each of them. So once we have Pascal's triangle, we're going to start a to the power of n, left to right. So in this case, we have x to the 4th, x to the 3rd, x squared, x to the 1st power, and then x to the 0 power. Now remember, anything to the 0 power is just equal to 1. Then we're going to do b to the nth power, but we're going to do it from the right side to the left side. So we'll have negative 3 to the 4th power, negative 3 cubed, negative 3 squared, negative 3, and then negative 3 to the 0 power, but reminding ourselves that anything to the 0 power is just 1. And now we get to simplify. Before we simplify, I want to take care of these exponents with a -3. So that's just 1. This stays -3. This becomes +9, -27, and +81. So we'll scroll down a bit. We will have to do some multiplying. So we have x to the 4th. Then we're going to have 4 times -3, so minus 12x cubed. Then we have to do 6 times 9. 6 times 9 is 54. So we have plus 54 times x squared. Then we have 4 times -27. 4 times -27 is -108 times x. And lastly, we have plus 81. So this was much faster than using the binomial theorem, but we got to the same result that we would have if we had used it by using Pascal's triangle to help speed up the process. So let's do one more example. This time we have 2x plus 3, and we want to go to the 5th power. So starting with, let's do orange. We have 1, 1, 1, 1, 2, 1, 1, 3, 3, 1. After you practice this enough, it becomes really automatic. And then I'm going to switch back to red, since 1, 5, 10, 10, 5, 1 is the row that we want. So once more, I'm going to space out as much as I can. 1, 5, 10, 10, 5, 1. And I'm going to put a plus sign at the start of each of them. And in a sense, these become my placeholders. Now let's do purple. We haven't used purple in a while. So A is equal to 2x. And we want to start with AN from left to right. So we have 2x to the 5th power, then 2x to the 4th power, 2x to the 3rd power, 2x squared, and then finally 2x. And we don't need to write it on the last one as long as we have it there as a placeholder. Because next, and let's do this bright green, we have b is equal to 3, and we're going to fill in bn from right to left. So we have 3 to the 5th power, 3 to the 4th power, 3 to the 3rd power, 3 squared, 3, and then nothing on this first term because 3 to the 0 power is just 1. The really fun thing is that we don't have to simplify very much because our calculators can do that for us. So I'm going to switch to a neutral color. 2 to the 5th power is going to be 32. So we have 32 times x to the 5th. Then I'm going to multiply 5 times 2 to the 4th power times 3, and that gives me 240. So plus 240 x to the 4th. Then 10 times 2 to the 3rd power times 3 squared is going to be 720 x cubed. Then 10 times 2 times 3 to the 4th. Oops, I just wrote 102, so let me fix that. So 10 times 2 times 3 to the 4th power is 1,620 times x squared. Then 5 times 2 times 3 to the 4th power is 810. So plus 810 times x plus 3 to the 5th power is 243. So it still took a minute for us to get there, but we were able to get there far faster than if we had used the binomial theorem. So on the remaining slides in the notes, you'll find the practice. If you scroll down, you'll see the solutions as well. And finally, you'll have the graded homework to finish you off on Go Formative. So with that, our lesson has come to an end, and our unit on sequences and series is finished.